Welcome to week number 15 for ECE 111. This week, we're going to be looking at Fourier transforms, solving differential equations where the input is periodic but not a sine wave. So in the ECE curriculum, you're going to be taking quite a bit of math. We're taking Calc 1, Calc 2, Calc 3, differential equations. The reason for that is differential equations pretty much describe the world. Circuits, weather, economics, ballistics, celestial mechanics, populations, disease spread, pollution, all that. Pretty much everything is described by differential equations. So differential equations are really fundamental to pretty much everything. Likewise, being able to solve differential equations is important. It's the topic that you cover in Calc 3, Calc 4. It's covered in Circuits 2, Signals and Systems. That's how to solve differential equations. The solutions to differential equations will be used throughout the curriculum in ECE. So solving differential equations is really, really important. Now, what we've looked at is how to solve differential equations with sinusoidal inputs. That's what we did last week. Last week we looked at using phasors. That's also covered in Calculus 3. Now the approach used in Calculus 3 is a little bit cumbersome. What you do in Calc 3 is given a differential equation, such as this one right here. If you know what the input is, the approach used in calculus is to guess the answer. If you guess right, you can solve. Guess wrong, the terms don't balance, you got to guess again. In this case, just from experience, I know that if the input is a sine wave at 6 radians per second, the output will also be a sine wave at 6 radians per second. It'll have a cosine term and a sine term. I've got two parameters I have to find. To do that, I need two equations, two unknowns. The way you come up with those equations is you take the derivative of y, which is this. If you haven't had calculus yet, just take it on faith. But when you do get to calculus, you'll take the derivative, which gives you sine and cosine term. Take the second derivative, then substitute. This goes in for y, this goes in for y prime, this goes in for y double prime. When I do that, I'll have cosine terms and sine terms. They both have to match up. That's my two equations, two unknowns. I get one set of equations for sine, one set of equations for cosine. Solve for a and b to make it balance, and that's your solution. Now that's about a 20-minute solution, kind of a painful way to do it. There is an easier way to do it. That's covered in Circuits 2. What we covered last week in this class. That's using phasors. Phasors is a way to represent sine waves using complex numbers. The advantage is you turn calculus into algebra, but it's algebra with complex numbers. For example, what we did last week is if we have this differential equation, I can rewrite it as this transfer function. Basically, s means derivative, so the numerator is times x, the denominator is times y. S squared means the second derivative of y, 3s, 3 times the first derivative, plus 8 times y. So that transfer function represents this differential equation. This is the gain everywhere. All I care about is what's the gain at 6 radians per second, so s is j6, times the input. In phasors, the real part is cosine minus j is sine, so 5 sine of 6t is 0 minus j5, 0 cosine, 5 sine. Analyze this, you get a complex number. What that means is the real part's cosine minus j is sine. So there's your answer. And here's what the input looks like, that's what the output looks like. Now what we did last week was use phasors. This is how to solve a differential equation when the input is a sine wave. Here's a problem for you. Suppose the input is not a sine wave. Well, a lot of signals are not sine waves. For example, kind of do a little bit of a sidelight. If you go to this website, MIDI, kind of a fun website. And what you have are musical instruments. Now what you see in the lower right corner, that is an app on my cell phone called Oscilloscope. That shows what the waveforms look like as I'm talking. So you have the different vowels. E, O. That's what vowels look like. If I play this MIDI, I can show you what a piano looks like. So that's what the waveforms look like for the different piano notes. And you can see different instruments. So for example, if I go to a harpsichord, that's the waveform for harpsichord. Try another musical instrument. How about tubular bells? Those are waveforms that are sine waves. Try another one. How about a bass guitar? Closer to a sine wave. Different instruments sound different. What you're seeing is the frequency content of the signals. The bass note is the note that you're playing, but there's other frequencies included, meaning that the waveform is not a sine wave. Tuba, oboe. Kind of a fun website. These are all periodic waveforms, but they're not sine waves. So here's another app called Spectroid. You can see the frequency content of the signal. See all those spikes on it? This is the frequency content of the signal. The 220 Hertz is the frequency that you're playing, but the other parts, the other spikes, show you what the frequency content of the signal is. Back to tubular bells. You see some very strong frequencies. I'm just kind of having fun with different instruments. So with musical instruments, the shape is not a sine wave. The shape tells you what kind of instrument it is, like a piano, tubular bell, cello. It also is the difference between the different notes. You have the different letters, a, e, o, u. Those have different shapes as well. The shape tells you what the sound is. So non-sinusoidal inputs are actually the norm. A few things have pure sine waves, like a whistle. A whistle is almost a pure sine wave. But other sounds are not. So how do you handle a periodic input that is not a sine wave? That's what this lecture is all about. So what we're going to do in this lecture is change the problem. And this is a really common engineering trick. If you have a hard problem to solve, change the problem. But change it in a way that makes the problem easier to solve, but keeps the flavor of the old problem. The change that we're going to use is a thing called Fourier Transform. That uses the property of linearity. If I have a differential equation and I have two components of it, I can analyze that differential equation for each part separately, add the two together, and that'll be the solution to the differential equation with both components. That's linearity. It's also called superposition. Once you have sine waves, we know, well, we're going to use that to approximate the periodic input as the sum of sine waves. Once you have sine waves, we know what to do. The last lecture we looked at using phasors. Using phasor analysis, I can find the output or the solution to the differential equation for each sine wave separately. I can then use superposition to add the two together to get the total response. This technique is called Fourier Transforms, named for Joseph Fourier. This is a topic that's covered in Circuits 2, Signals and Systems later on in the curriculum. Here, this is kind of an introduction class to electrical engineering. We're going to be using MATLAB to solve this type of problem. Kind of the goal is when you get to Fourier Transforms in Circuits 2, Signals and Systems, it'll be more familiar. First time is always the hardest. But the real goal of this class is using MATLAB. I can solve all sorts of problems. Here we're going to solve this type of problem using MATLAB. Try to find the output of a differential equation when the input is periodic. Now, Fourier transforms are actually really important. With Fourier transforms, you can solve any differential equation with any periodic input, and that's really powerful. In this lecture, I'm going to give a concrete example. For example, rather than just looking at circuits, let's look at something you run into in biomedical engineering. We're going to look at the cardiovascular system, basically the left ventricle, the aorta, and the capillaries going to the body. I'm going to model the cardiovascular system as a differential equation. I'm going to model the blood flow, the flow coming out of the heart when the heart compresses, as a periodic waveform that's not a sine wave. And then for that non-sinusoidal periodic input, try to find the aortic pressure. So that's kind of what we'll be doing. This really works for any differential equation with any periodic input. This is what we're going to look at, just to give us something concrete to look at. The first step is I need to come up with a differential equation. And here what I'm going to do is try to model the cardiovascular system, and the model I'm going to use is called the Windkessel model. What you do is you have a current source trying to model the heart. Current is the analog for blood flow. When the heart pumps, it squeezes and pushes out blood. That's your current. The first place the blood goes is the aorta. The aorta expands and absorbs the blood. That's like a balloon, or electrically a capacitor. It stores charge. The aorta then shrinks, pushes the blood through the body. The blood has inertia. The analog of that, of inertia, is inductance. Keeps the blood flowing. And that blood flow then goes to all the capillaries to the body. Model that as resistance. There's more complicated models. This is probably the simplest model for the cardiovascular system, called the Windkessel model. This is what we'll look at in this class. So given this, I know the current, I want to find the voltage, meaning I know the aortic flow. I want to know left ventricle pressure. Well, to do that, I'm going to be using phasors and Laplace notation. For resistors, the impedance of resistors is just R. Inductors are j omega L, and let's just use S for j omega. Makes the notation a bit easier. S means j omega, also means derivative. Capacitor is 1 over j omega C, or 1 over CS for short. So here, the impedance is 1 over CS. This impedance is LS. Here's R. The total impedance, looking in, is capacitor in parallel with an RL circuit. So that's 1 over the impedance of a capacitor, 1 over CS. Plus these are in series. In series they add 1 over LS plus R. Take the inverse, that's the total impedance. Doing a little bit of algebra, putting this over common denominator, gives you LS plus R over CLS squared plus CRS plus 1. What that impedance tells you is that if I know the current, I times R, I times E is voltage. Current times this transfer function gives you voltage. So if I plug in a number, just kind of chose at random, R is 1, C is 1, L is 0.1, gives you this as the transfer function. That'd be the transfer function from current to voltage, or this is the differential equation that relates current and voltage. So that's the first part of this problem. I need to come up with a differential equation that I want to solve. This differential equation describes the cardiovascular system for a person with these parameters, let's say. So if I know the aortic flow, or AOF, left ventricle flow, I can tell you what the left ventricle pressure is, aortic pressure is, through this differential equation. Now coming back to this lecture, suppose I is periodic. How do you find V? Well, that kind of depends. If the current is a sine wave, then I can find the voltage using phasors. So for example, suppose current is 3 sine of 10t. This is a phasor problem. This is the gain everywhere. All I care about is what's the gain at the frequency of the input. Frequency of the input is 10 radians per second. So analyze this at s equals j10. In phasor form, the current is a complex number. The real part's cosine minus j is sine. So this has 0 cosine part, 3 sine. This is the phasor form of current. Multiply them all together, I get a complex number. What that means is the real part's cosine minus j is sine. So that's how I would find the voltage given the current if the current is a sine wave. Now, as you probably know, the heart doesn't flow like this. The heart actually kind of pumps. And it's more like what the aortic flow looks like. Given that, what's the pressure? Now I'm going to change the problem a little bit. Rather than doing what the actual aortic flow looks like, let's kind of simplify it. Let's just do a square wave. That's easier to input into MATLAB. Kind of the same idea though. So let's just assume this is the aortic flow. That's the current for this circuit. If this is the current, find the voltage. Now I'm going to assume that the current is periodic. It repeats every 2 pi over 10 seconds. That just means that I of t plus 2 pi over 10 is I of t. Just repeats over and over again. Here's a periodic input that is not a sine wave. Try to find the voltage for this input. Well, again, what we know is if the input was a sine wave, I would know what to do. But this is not a sine wave. How do we handle this problem? Well, one approach is to change the problem. I have x of t is a square wave. That's hard to work with. Let's do a curve fit. I can curve fit pretty much anything. We've done that before a couple times. Suppose I did a curve fit where I expressed the current in terms of a power series. So A0 plus A1t plus A2t squared, A3t cubed, and so on. In MATLAB I can do that. Here's my time. It goes from 0 to 2 pi over 10, one period. X is 1 for the first 200 milliseconds. Again, it kind of repeats. Here's one cycle. I'm just doing this part right here. That's one cycle. Then it repeats. Here's my basis, 1t, t squared, t cubed. Then a least squares curve fit. We've done this a bunch of times. The least square solution is inverse of b transpose b transpose x. Gives you the coefficients. So this is the first basis element. That's your constant term. Here's the next one. The t term, t squared, t cubed, t to the fourth. Plot these two together. It's not a perfect match. Add more and more terms, it gets better and better. I now have a series expansion for x of t. Now, a problem with this solution is it doesn't help. I know what to do with differential equations when the input is a sine wave. I don't know what to do when the input is a power series. So here's a curve fit series expansion. I can do that. I can curve fit anything, but the solution doesn't help. Let's try that again. Rather than using a power series, let's use a bunch of sine waves. Let's approximate x of t with a DC term, first harmonic, second harmonic, third harmonic. Here, omega naught, well, the period, is 2 pi over 10 seconds. The omega naught, fundamental frequency, is 2 pi over t, or 10. What this basically says is if I have a bunch of sine waves that are at 10, 20, 30, 40, harmonics at 10, they have a period of 2 pi over 10. They repeat every 2 pi over 10. If I add all those up, the result will be periodic in 2 pi over 10 seconds. So this is just another way of expressing x of t. I'm going to take a bunch of waveforms that are also periodic in t, add them all up, I get x of t that is also periodic in t. Now, this is just a curve fit. I can curve fit anything. The advantage of this basis, or this solution, is my answer winds up being sine waves. I like that. I know what to do with sine waves. That's the whole reason for doing this. This is called the Fourier Transform. It's no different than any other curve fit. The only difference is I choose a very specific basis. My basis is a bunch of sine waves. So this is what Fourier transform is. Assume x of t is periodic in t seconds. Then x of t is a DC term plus a bunch of sine and cosines, where each sine wave is a harmonic of the fundamental. The fundamental is 2 pi over t. What that means is if I go right to left, if I take a bunch of sine waves that are periodic in t seconds, the answer is periodic in t seconds. That's kind of like a no-brainer, like the. The other way is actually kind of interesting. If x is periodic, it has harmonics. That's the powerful part of Fourier transform. And that's kind of what's showing up over here. This is showing the frequency content of the sound that's going on in the room. So as I speak, you can see the frequency content of my voice. When I do vowels like e, o, oo, those are not sine waves. These are the harmonics of them. The different harmonics give you the different vowels. If I whistle, a whistle's a pretty clean sine wave. If I do instruments, like these are tubular bells, those are the different frequencies that make up the waveform. And the waveform again, going back to the oscilloscope app, these are the vowels. E, O, oo. Those aren't sine waves, meaning they have harmonics. Or the tubular bells. That's Fourier transform. Equals is a really powerful symbol. It means these two sides are identical. Periodic waveforms create a periodic waveform. If x is periodic, it has harmonics. Now, there's a couple ways to look at this. I can go left to right, right to left. How do I go right to left? How do I create different wave shapes by adding up sine waves? Well, you can go to several different locations. Wikipedia does this. The CRC Handbook of Mathematics does it. It gives you the formula. If I add up these harmonics, I get a square wave. Add up harmonics with these weightings, 1 over n squared for n odd, I get a triangle wave. This produces a sawtooth wave, half rectified sine wave, a fully rectified sine wave, and so on. I can see that in MATLAB. So MATLAB, here's a script. It just uses those weightings that are from CRC Handbook of Mathematics and starts adding them up. I start with the DC term, add in the first harmonic, second harmonic, third harmonic. Each harmonic is a multiple of the fundamental. Here the fundamental is 2 pi, 1 radian per second. The reason I did that is because 1's a nice number. I'm going to add up the harmonics as 1 over n. If I do that, I get a square wave. And as I add more and more terms, here's the first harmonic, first 3, adding up the odd harmonics. The more I add, the closer it gets to a square wave. Go to infinity, I get a square wave dead on. Okay, let's try triangle wave. For a triangle wave, harmonics drop off as 1 over n squared. If I try that, first harmonic, see very quickly it converges to a triangle wave. In theory, I have to go out to infinity. That's to get the really sharp corners at the peak and bottom, go out to infinity. But pretty quickly, I get pretty close to a sine wave. Triangle waves have harmonics that drop as 1 over n squared. Let's try a sawtooth wave. Sawtooth wave, they drop off as 1 over n squared. 1 over n minus 1. Oh, starts off as 1 over n. Try that again. This doesn't converge quite as fast as the triangle wave. That's because the harmonics drop off as 1 over n rather than 1 over n squared. Keep on going, eventually converges to a triangle wave. Half rectified sine wave. This is more complicated. It's got a first harmonic and then even harmonics from then on. So that's kind of one way to go right to left. You use Wikipedia or some other table. You can look up the Fourier transform for different waveforms. And it works. If I add them all up, going out to infinity, I get the waveform exactly. As I add more and more terms, I get closer and closer to that desired waveform. So that's going right to left. Given the equation, come up with x of t. And what's not too surprising is that sine of nt is periodic in 2 pi. So the answer is periodic in 2 pi. So not too surprising. Add up waveforms that are periodic. The answer is periodic. That's going right to left. And that's kind of what I showed you. Here's a square wave. If you have infinite terms to get the blue line, only the first 9th harmonics gives you the red line. They're fairly close. Triangle wave, infinite terms, the blue line. The first 9 harmonics are the red line. Half rectified sine wave, infinite terms, the blue line. First 9 harmonics, the red line. Not perfect. These corners are where you get the high frequency terms. The sharper the corner, the more the high frequency terms. But that kind of shows that I can go right to left. If I add up these waveforms, the answer is a periodic waveform, triangle wave, square wave, sawtooth wave, half rectified sine wave. That's going right to left. Here's a problem for you though. How do I go left to right? Well, one solution is least squares. I can curve fit anything. So let's go back to our original problem. I've got blood flowing through the heart. The blood is periodic. The period right here is 2 pi over 10 seconds. Come up with a series expansion using sine and cosine waves. So since this is periodic in 10 radians per second, let's have a DC term and sine and cosine terms that are multiples of 10 radians per second. I'll have the first harmonic, the second harmonic, and so on. In theory, go out to infinity. Here I'm just going to go out to the second harmonic, call it good. So to do that using least squares, I would rewrite this in matrix form. Here's my basis function, 1 cosine sine at 10 radians per second, cosine sine at 20 radians per second. Here's my constants. That's my basis function b. To find my constants, I would do least squares curve fit. Inverse of b transpose b times b transpose y. Here, let's see, y is actually my current. That would say that the current has a DC term, sine and cosine for the first harmonic, sine and cosine for the second harmonic. So using MATLAB and least squares curve fitting, I can come up with a sine wave approximation to the current, the input. If I plot it, and MATLAB can plot that as t versus I, that's the blue line, t versus my curve fit, the curve fit is b times a, that's the red line. It's not perfect. As I add more and more terms, it'll get better and better. But what that means is, at least going into the second harmonic, this is I of t. Now what's significant is now the current is in the function of sine waves. I've got a DC term, 10 radians per second term, 20 radians per second term. That's good. I know what to do with sine waves. I can use phasors to find the output, find the voltage at each frequency. That's the whole point of Fourier transforms. Take the input that's periodic but not a sine wave, turn it into a sine wave. That was only with 2 terms. If I went out to 20 terms, this is what it would look like. So the more terms you add, the better the approximation. A second way to get the terms is called Fourier transform. Now here's what the current looks like. I've got a DC term, 10 radian per second term, 20 radian per second term. A property of sine waves is all sine waves are orthogonal. This is an orthogonal basis. When you take Math 129, linear algebra, they'll talk about orthogonal basis, orthonormal basis. This basis is orthogonal, but it's not orthonormal. What orthogonal does is I can find the terms separate. They're orthogonal, they don't interact. For example, to find the A0 term, what I'll do is I'll take this guy and find the average. The average of sine is 0. The average of cosine is 0. Take the average, all these terms go away. What I'm left with is A0. So A0 is just the average of I of t. To get the other terms, like A1, what I'll do is take this function, and instead of just find the average, I'm going to hit this with, let's take this term right here. Hit that with sine of 10t. Now all sine waves are orthogonal. The average of sine is 0, so this term goes away. Average of sine times cosine is 0. Let's show that. I'm just going to plot a sine wave out to 4 pi, 2 cycles. And let's plot t versus sine times cosine. Going to see pretty obviously it's symmetric about the 0 line. The average is going to be 0. Let's do sine of t times cosine of 2 times t. That also averages out to 0. So these two parts cancel, these cancel, everything cancels, the average is 0. Let's do sine of t times cosine of 3t. Again, averages out to 0. Cosine of t times cosine of 2t. Average out to 0. Cosine times 3. Do that with the mean function. Sine and cosine, the average is basically 0. Cosine times sine of 2t, 0. Sine of 3t. Cosine times cosine. Cosine of t times cosine of 2t, average is 0. Times 3, average is 0. 4. And the reason it's not 0 is I'm double counting the two endpoints. So we'll have one double count them. If I do that, I get 0. So all sine waves are orthogonal. The time where it's not orthogonal is to have cosine squared. That average is 1. Average of sine squared, that's actually half, is a half. And when you plot it, if I do cosine of t times cosine of t, cosine squared is always above 0. It goes 0 to 1, 0 to 1. Kind of by symmetry, the average is a half. The average of sine squared, sine squared goes 0 to 1, 0 to 1. Average is a half. So to pick out the terms, to pick out this term, I'll multiply by sine of 10t. All these terms go away. What I'm left with is a half times b10. If I want to pull out the A20 term, what I'll do is multiply I of t times cosine of 20t. That'll pull out this terms. All the other terms go away. And the answer will be 1/2 A20. That's kind of a shortcut. This works because the basis is orthogonal. This basis element averages out to 0 for all the other terms. That means orthogonal. It's not orthonormal. When I multiply this, I don't get 1. I get a half times A20. So using these properties, all sinoids are orthogonal. Sine times cosine is 0. Sine times sine is 0. Unless A equals B, then it's a half. Cosine times cosine is 0. Unless A equals B, then it's a half. What that does then is I can find the different terms. It's twice the average of I of t hit with cosine 10t. B10 is twice the average of I of t hit with sine of 10t. And likewise for second harmonic, third harmonic, fourth harmonic, and so on. In MATLAB I can do that. Here's the DC term, just the average. The cosine of the first harmonic, sine at 10t, cosine at 20t, sine at 20t. And the net result is exactly what I got before. So Fourier transforms is no different than least squares curve fitting. All I'm doing is I've got a periodic signal, I'm doing a curve fit. I just choose my basis to be sine waves and cosine waves. If I do that, I'll get the same answers I do with Fourier transforms. The advantage of Fourier transform is this is actually a more efficient way of doing it. Same answer though. So at this point I have a sinusoidal representation of my input, I of t. Find the output, find the voltage. Well, here's where I use superposition. Superposition states that if I have a differential equation with 3 inputs, I can treat that as 3 separate problems. Find f of A, f of B, f of C, add 3 answers together, that will be your total answer. So at this point I have 3 different currents. I have the DC term, 10 radian per second term, 20 radian per second term. That's these guys right here. There's the DC term, the term at 10 radians per second, term at 20, and there's one at 30, 40, 50. I'm just using these 3. Treat that as 3 separate problems. I'm going to find the output, assuming the input is DC. Find the output, assuming just using the 10 radians per second term. Find the output for the 20 radians per second term. Add them all together. That's my voltage. So in MATLAB, here's what you do. I've got my time. Here's x of t. My frequency is s equals 0. A0 is just the average of x. That's my current. Here's the gain. The gain of my system is s plus 10 over s squared plus 10s plus 10. Find the gain at 10 radians per second. The gain times the input is the output. So here's the gain, here's the input, there's my output. What that tells me is here's the DC term for my voltage. First part of the solution. Second part of the solution, at 10 radians per second. Here's my frequency, s equals j10. Find the cosine term, find the sine term. In phasors, the phasor representation for sine wave is the real part's cosine minus j is sine. So there's the phasor representation current. Here's the gain. Find the gain at 10 radians per second. Gain times input is output. There's my voltage. And what that means is this is my voltage at 10 radians per second. Real part's cosine minus j is sine. At 20 radians per second, same thing. Now s is j20. Here's the input at 20 radians per second. Cosine part, sine part. In phasor form, real part's cosine minus j is sine. So there's I of t in phasor form. Here's the gain at 20 radians per second. Output is gain times input. So there's my voltage right here. Real part's cosine minus j is sine. Add them all together, and that's my voltage. So there's the DC term, 10 radian per second term, 20 radian per second term, or DC term, first harmonic, second harmonic. That's V of t. Now in MATLAB, going to show you what that looks like. I can keep on going. So here I'm going to go out to 10 harmonics. I didn't do that in lecture notes because it gets kind of tedious. But once you have it in MATLAB, if I can do 2 harmonics, throw it in a for loop, and I can do 10, 20, 30, 40. Here's what it looks like. So the input is blue. The output is red. This is the output after 5, 6, 7, 8, 9, 10 harmonics. Let's do that again. DC, first harmonic, second, third, fourth, fifth. In theory, I need to go out to infinity. In practice, it doesn't do a whole lot of difference. This is the beauty of for loops. I can keep on going. You kind of see, once you get past about 4 harmonics, it doesn't make a huge difference. They're there, but not a huge difference. What's really significant is I now found the output of a differential equation where the input is periodic, but it's not a sine wave. And this approach works for any type of input. For any input, if it's periodic, it has harmonics, find the frequency content, find the output at each frequency, add them all together, I get the total output. So this is a pulse with width of 0.1, change that to 0.2. Okay, nothing really changes. Once you have x of t, find the frequency content, go through all the harmonics to find out what it is. Let's try a different x. This is a half-rectified sine wave. If that's your input, again, I didn't change the algorithm at all. I'm going to take the periodic input, the blue line, find its frequency content. Once I know the frequency content, find the output at each frequency, add them up, I get the total output. This is a really universal approach. Let's do a triangle wave. If that's x, actually jumps, that's a sawtooth wave, I get the output as well. So a very universal solution. That's the power of Fourier transforms. I can now solve differential equations for any periodic input. So in the handout, here's a problem for you. Suppose x and y are related by a differential equation or transfer function, same thing. If this is the input, find the output. And pause the video and see if you can come up with the answer. Okay, picking up, what I would do is I would solve this in 3 parts. Let's bring up MATLAB. I would have a DC term, something at 4 radians per second, something at 6. At DC, s equals 0, x is equal to 2. And let's do it this way. Here's the DC term. Y0 is the gain, 20 over s plus 10, times x0. There's the DC term. At 4 radians per second. There, s equals J4, or 4i, MATLAB speak. X4 is 3 plus J0, 3 cosine, 0 sine. Y4 is then the gain, 20 over s plus 10, times x4. Real part's cosine, minus j is sine. At 6 radians per second. So adding those together, so y of t That's the first part. That's the DC term. The second one, 5.17, that's the real part, cosine of 4t. Complex part is the sine part, 2.06 sine of 4t. To get the last part, at 6 radians per second, I'd have S equals J6. X6 is equal to 0 minus phi by. Again, real part's cosine minus J is sine. Y6 is the gain times the input at 6 radians per second, minus 4.41 cosine of 6t. And the complex part, 7.35 plus 7.35 sine of 6t. That's superposition. If I have 3 separate frequencies, treat those as 3 separate problems. Note a mistake that students oftentimes make is they'll take these 3 answers. I've got y0, y4, y6, and add them. If I do that, y0 plus y4 plus y6, I get a complex number. That number is complete nonsense. Why it's nonsense is these are 3 separate frequencies. I can't take 4, add it to cosine and sine and get a number. The frequencies are different. It doesn't simplify. The DC term is separate from the 4 radian per second term, is separate from the 6 radian per second terms. You can't add the answers together. In phasors, these are complex numbers. It looks like you can add them together, but you can't. They're different frequencies. Last thing to mention is how many terms do you need? Well, in theory, the answer is infinity. In practice, I can get by with typically just 2 terms. The reason for that is most signals are dominated by a few low frequency terms. Most filters are low-pass filters. Put the 2 together, you get something like this. The output, almost all the energy is in the first 2 harmonics, the DC and the first harmonic. All these terms really don't matter all that much. Typically what you want, especially in electronics, is I've got a signal that's got a little bit of ripple on it. There's a DC value, and there's the ripple. This tells you the DC value, the average. This tells you the ripple. And technically the ripple's not a sine wave. It's got some distortion on it. That's what these tell you. If all you care about is the peak-to-peak ripple in the DC term, that's usually sufficient. I'm going to be a little bit more accurate, maybe include a couple more harmonics. What we saw over in MATLAB, kind of like here. But just include the first DC and the first harmonic that pretty much captures the waveform, that pretty much had the DC value and the ripple peak to peak. The ripple's not exactly a sine wave. Include a couple more harmonics. I can see that's actually more of a triangle wave. If you care. Oftentimes you don't care. I just want to know what's the ripple, what's the DC value. And that's the saving grace. In theory, you got to go out to infinity. Infinity is a tough number to work with. In practice, if you just include a couple of harmonics, sometimes go out to the 5th harmonic, oftentimes just the first 2. That's good enough. So that is Fourier transforms. Again, it's kind of intimidating. It's something you're going to get to when you get to signals and systems. You might get to it in circuits and electronics. Really, it's not all that bad. Once you have phasors, once you have superposition, you have Fourier transforms. Fourier transforms allow you to solve any differential equation with any periodic input. That's really powerful. All you have to do is express the input in terms of DC terms and harmonics, find the output at each frequency separately, add the results together to get the total output. It's a little bit tedious. It includes a lot of terms. Not too bad in MATLAB. Just throw it in a for loop. but typically just a few terms are sufficient. What's significant about that is this works. You can get an answer for any periodic input. That's really powerful. And that is lecture number 15 for ECE 111, Fourier Transforms.